I will not get tired of repeating that our solar system is an absolutely fascinating place. Each planet, moon, dwarf planet, or even asteroid is unique and interesting in its own way. The more we learn about them, the more we yearn to explore our closest celestial neighbors. In this thematic collection on the channel, I invite you to embark on a journey to the most extraordinary moons of the planets in our solar system, the water geysers of Enceladus and Europa, the volcanoes of Io, and the methane rivers and lakes on the surface of Titan. We will discuss all of this and more over the next 80 minutes, so make yourself comfortable and enjoy the viewing. On July 1, 2004, the spacecraft named Cassini-Huygens was launched into orbit around Saturn. Launched in 1997, this spacecraft aimed to comprehensively study Saturn and its system, including the legendary rings of the planet and its moons, which have sparked special interest among scientists. The mission team hoped to discover previously unknown satellites of the gas giant and learn something new about the ones already known. For instance, they were curious if there are oceans on the surface of Titan, Saturn's largest moon, and what chemical reactions take place in its atmosphere. To achieve this, Cassini-Huygens was equipped with a special probe, successfully descended to the surface of Titan, sending back a wealth of important scientific data to Earth. However, undoubtedly, one of the mission's top priorities was to explore the tiny but incredibly bright moon of Saturn, Enceladus. This mysterious world had intrigued scientists since the Voyager 2 mission, which flew past the Saturn system in 1981. After 26 years of anticipation, the new spacecraft approached the moon again, making stunning discoveries. Near the south pole of the icy Enceladus, massive geysers of water vapor and ice particles were erupting through giant fissures. Scientists concluded that beneath the surface, there must be a global ocean of liquid water. Subsequent analysis of the material ejected by the geysers led researchers to consider Enceladus as one of the most suitable places for extraterrestrial life beyond Earth. Enceladus is a relatively small moon, only 500 kilometers in diameter. Two such objects would easily fit within the territory of Ukraine. However, it is exceptionally bright due to its extraordinarily smooth and brightly white surface. It is the most reflective body in the solar system, with almost 100% of solar radiation being reflected back into space. Therefore, it's not surprising that the surface temperature is very cold, never rising above -2 degrees Celsius. Discovered in 1789 by the English astronomer William Herschel, Enceladus was named after one of the giants in Greek mythology. Yet until a Voyager 2 mission visited the Saturn system in 1981, little was known about it. Upon closer examination, Voyager 2 made the first detailed images of Enceladus' surface. The images reveal areas where impact craters were entirely absent, indicating a relatively young age of the surface. Conversely, there are also regions with numerous craters, similar to other Saturnian satellites. Some areas appeared as if they were eroded by geological activity. The highly reflective nature of Enceladus' surface also suggested a constant renewal process. This was further supported by its low gravitational attraction, which indicated a porous structure. The bright surface would have darkened over millions of years due to meteoritic dust settling on it, but the continual activity seemed to be cleaning and renewing the moon's appearance. The discovery of water geysers erupting from the surface of Enceladus confirmed these suspicions and raised the question of how such geological activity is possible on this tiny and icy sphere. Geological activity on Earth is caused by the initial heat remaining from the planet's formation and the decay of radioactive elements. Due to its size and relatively close proximity to the Sun, Earth is still hot and slowly cooling. We live on a thin outer shell, the Earth's crust, under which lies a more plastic and very hot mantle that can move due to convective processes. In other words, hot material rises, and cold material, conversely, sinks. This convective flow in the mantle causes the movement of lithospheric plates on the surface, leading to constant changes in the outer shell of our planet. However, Enceladus is just a tiny moon relative to Earth and is at a colossal distance from the Sun. Therefore, its geological activity must be caused by something else, some internal source of energy. The reason, it turns out, is not in the moon itself but in its giant parent planet, specifically in its powerful gravitational force. Enceladus orbits Saturn at a distance of 238,000 kilometers between the orbits of its two other moons, Mimas and Tethys. Similar to our moon's relationship with Earth, Enceladus is tidally locked to its planet, completing one rotation around Saturn every 33 hours. Additionally, like many other moons in the extensive systems of giant planets, Enceladus falls into a so-called orbital resonance. This occurs when two or more moons align with the parent planet at regular intervals and gravitationally interact. Enceladus revolves around Saturn twice for every one orbit that Dione, a moon twice its size, completes. The gravitational force of Dione influences the orbit of Enceladus, stretching its elliptical shape. As a result, Enceladus periodically moves closer and then farther from Saturn, causing tidal heating inside it. When Enceladus approaches Saturn, the colossal gravitational force of the planet literally stretches the icy moon. As it moves away, the moon compresses again. These constant deformations cause friction and, consequently, heating within Enceladus. Therefore, Enceladus is an active world. Detailed photos of its south polar region taken by the Cassini probe revealed a territory devoid of impact craters and covered with tectonic fractures and ridges. Near the center of this region are four massive fractures unofficially named tiger stripes. In detailed infrared images, it is clear that these stripes are warmer than the rest of the surface, showing a reddish color due to fresh ice deposited after eruptions. The tiger stripes are the sources of water jets erupting from the surface, appearing as continuous eruptions forming a massive halo of fine ice dust around Enceladus. Most of the material returns to the surface like snow, helping the moon maintain its bright white color. However, some of the ice escapes into space, forming Saturn's broad outer ring known as the E ring. By the way, the origin of the ring was one of the mysteries of the gas giant. According to mathematical models, the ring could hardly be stable. That is, without constant replenishment of material, it could not have existed for long. In the 1980s, scientists suspected that Enceladus might be connected to the ring as the tiny moon moves close to its center. However, it was only in 2005, during the first two close flybies of Cassini, that it was confirmed. Enceladus is indeed the primary source of ring material, as Cassini detected a significant increase in the number of ice particles near the moon. Later, with photos taken by Cassini, it visually captured how jets of particles rise from Enceladus' south pole. Eventually, it became clear that Enceladus is the main supplier of material to the ring. By 2010, scientists believed that the ocean fueling the geysers on Enceladus was limited only to the south pole. However, through gravity measurements of the moon and observations of its slight wobbles during orbit, scientists determined that the entire icy crust of Enceladus is actually separated from the rocky core. Thus, the jets are supplied by a global ocean inside. Researchers believe that the icy shell of Enceladus at the South Pole may be relatively thin, no more than a few kilometers. However, the average thickness of the ice covering the moon is estimated to be between 20 to 25 kilometers. The depth of the subsurface ocean ranges from 26 to 31 kilometers. For comparison, Earth's ocean has an average depth of almost 4 kilometers, which is 7 times less. But what might that extraterrestrial ocean hide? Throughout the Cassini mission, it repeatedly flew close to Enceladus and even directly dove into geysers erupting from its surface. Chemical analysis of the substance it managed to capture showed very intriguing results. It turns out that at the bottom of the global ocean beneath the icy crust, there are likely active hydrothermal vents that could create ideal conditions for the comfortable existence of microorganisms and even more complex fauna. Somewhere on the seafloor of Earth's oceans, water seeps deep into the ocean floor where rocks are heated by hot magma. Hydrothermal vents, places where mineral-rich water erupts from the seafloor back into the ocean, are created. This water contains so many fine particles and dissolved minerals that it looks like smoke. That's why these openings resembling chimneys are called black smokers, and their counterparts, emitting white smoke, are called white smokers. Black smokers are usually hotter, with temperatures around 350 degrees Celsius, and their smoke is black because it's rich in iron and other metals. White smokers are less hot and are rich in minerals composed of calcium and magnesium. The main feature of both types of hydrothermal vents is the vibrant ecosystems that thrive in the warm water, rich in minerals. In fact, a complete biogeosynosis of large colonies of archaea and other more complex organisms, such as shrimp-like worms and mollusks, was discovered here. Therefore, life is bubbling in such places entirely independently of the rest of the world. Scientists were undoubtedly a bit shocked when they found evidence of active hydrothermal vents in the ocean beyond Earth. Using a cosmic dust analyzer installed on Cassini, researchers were able to detect tiny pieces of rock. These were crystals of silica, indicating that they were formed in a saline ocean of rare water at a temperature of at least 90 degrees Celsius. Black smokers on Earth create similar conditions, and scientists also noted a high amount of methane in the trail, which is hard to explain with anything other than the presence of hydrothermal vents. The third evidence for scientists turned out to be molecular hydrogen, which can be formed as a result of geochemical reactions between water and rocks. Unfortunately, the Cassini probe, launched in 1997, was equipped with technology of its time, and researchers then did not know about geysers and oceans on Enceladus or about hydrothermal vents on its seafloor. Therefore, Cassini did not have instruments capable of detecting signs of life, such as proteins. But undoubtedly, Enceladus is worth visiting again, and this time with a full-fledged astrobiological mission. Especially since this world is still within the solar system, so its exploration should not be a big problem. In case traces of the simplest life are discovered, we will immediately look at the universe differently. After all, if even such cold, tiny worlds can harbor life, then it must be everywhere. Moving on to Saturn's largest moon, Titan, which is undoubtedly an extraordinary and exceptional world among over 150 known moons in our solar system. Titan is the only one with a solid atmosphere. It is, in fact, the only place beyond Earth known to have liquids on its surface in the form of rivers, lakes, and even seas. Titan is Saturn's largest moon, and it is another icy world, but its surface is completely obscured by a golden hazy atmosphere. The moon is 50% larger than our moon and 80% more massive. It is even larger than the planet Mercury and is the second largest moon in the entire solar system. Titan's atmosphere is mainly composed of nitrogen, a gas that, by the way, you are currently inhaling into your lungs because it is a major component of Earth's atmosphere. However, unlike our planet, Titan's atmosphere does not contain oxygen. Instead, the moon has clouds, rain, rivers, lakes, and seas. But of rare water and liquid hydrocarbons such as methane and ethane, the largest seas are probably hundreds of meters deep and hundreds of kilometers wide. It is anticipated that beneath Titan's thick crust, there may be a gigantic ocean, but not of methane, mainly composed of rare water. Saturn's largest moon was discovered in 1655 by the Dutch astronomer Christian Huygens, who was inspired by Galileo's discovery of Jupiter's four largest moons in 1610. For a long time, Titan was considered the largest moon in the entire solar system, larger than Ganymede. However, this estimate was exaggerated due to its dense, opaque atmosphere. In 1980, it was examined by Voyager 1, which determined that a layer of dense yellow haze extends above the surface for 100 to 200 km, significantly increasing the visible size of the moon. The pressure of this atmosphere is about 60% higher than on Earth, giving the sensation of floating in Earth's ocean at a depth of 15 meters. As for the chemical composition, Titan's atmosphere is 95% nitrogen and about 5% methane, with a small fraction of other carbon-rich compounds. It is believed that hydrocarbons are formed in the upper layers of the atmosphere in reactions caused by the breakdown of methane by sunlight, leading to the formation of a dense orange smog. Interestingly, this gaseous methane can condense, forming clouds from which liquid methane droplets can fall to the moon's surface as real rain. These methane rains erode Titan's surface, carving channels and flowing into basins, creating real methane seas and lakes. Over time, the liquid natural gas evaporates back into the atmosphere, completing a cycle similar to the water cycle on our planet. Due to the dense atmosphere and lower gravity, methane rain on Titan looks a bit different from Earth's rain. Firstly, the droplets fall more slowly on Earth. Their speed is about 9 meters per second, while on Titan it does not exceed 1.5 meters per second. Secondly, the raindrops on Titan are larger than those on Earth, approximately 30% larger. The methane in Titan's atmosphere is what enables its complex atmospheric chemistry. But where does all this methane come from? The puzzle arises because solar light continually breaks down this compound in the atmosphere, and methane should have run out over millions of years. Therefore, there must be some source replenishing it. One of the possible sources scientists refer to is cryovolcanism, a special type of volcano in conditions of extremely low temperatures. Instead of molten rock, they erupt water, ammonia, and methane in liquid or gaseous form. However, the exact origin of methane is yet to be determined, possibly through future missions to the Moon. Despite 2 flybies by the Voyagers near Titan, astronomers knew little about its surface until Cassini arrived in the Saturn system in 2005. The cameras on Voyager could not see the surface through the thick orange smog in the atmosphere. Still, Cassini was equipped with instruments that, at certain wavelengths, could peek through the dense orange blanket. The spacecraft even sent a special module called Huygens to the surface, providing us with a historic panorama of Titan's surface. Although small in part, Huygens conducted atmospheric composition measurements and, of course, took photos of the surface. The robust probe not only survived the descent and landing, but continued to transmit data for over an hour on the frigid surface until its batteries were finally depleted. Thanks to Cassini and the Huygens module, astronomers could finally observe Titan's surface, about which they knew nothing since the Moon's discovery in the 17th century. It turned out to be the most Earth-like place in the entire solar system, but with significantly lower temperatures and different chemistry. There are plains, mountains, lakes, and even dunes like in Earth's deserts. It's so cold that water ice serves as the rocky material. The surface around the Moon's equator features large areas of dark dunes, seemingly caused by wind-blown particles of dark hydrocarbon grains settling on the surface from the atmosphere. In these dunes, composed of dark hydrocarbon grains, Titan's surface appears like genuine rocky cliffs. Near the equator, there are extensive regions of linear dunes that are no different from those observed, for example, in the Namib Desert in Africa. However, no dunes or icy rocks are as impressive as the giant lakes and seas on the Moon's surface. Undoubtedly, no other world in the solar system except Earth has anything similar. It is worth noting that the lakes do not cover the entire surface of Titan, but are mostly concentrated near the poles, where the relative lack of sunlight hinders their evaporation. The first large surface lake on the Moon, named Ontario Lacus, was discovered near the South Pole. It has an area of 15,000 square kilometers, only 20% smaller than its well-known Earth counterpart, located in North America. Ontario Lacus consists of liquid methane, ethane, and propane and appears extremely shallow. Radar measurements indicate an average depth ranging from 40 centimeters to 3 meters. The largest lake in the southern hemisphere is much larger. The deeper hydrocarbon sea, with the epic name Krakenmare, covers a colossal area of 500,000 square kilometers. It is the largest known sea on the surface of Titan, even surpassing Earth's Caspian Sea. However, determining its depth proved challenging. For this, the Cassini probe needed to send a radio signal that would reflect off the surface of the liquid and the seabed. Yet, Krakenmare turned out to be so deep that the radar signal couldn't reach its bottom. Estimates of its depth are still conflicting, ranging from 35 to 300 meters. Interestingly, in the northern part of this vast sea lies an island named Matensula. This is the first island discovered on another celestial body. The second largest seen on Titan, Valles Marineris, was discovered in 2013 and surprised scientists with its peculiar properties. Typically, seas and lakes on Titan appear dark, but Cassini revealed exceptionally bright anomalies in Valles Marineris, which after further observations, seemingly disappeared. The origin of these mysterious magic islands, as scientists jokingly called them, presented an intriguing puzzle. However, they eventually realized that these islands were just nitrogen bubbles erupting from the sea's depths. These bubbles strongly reflected radio waves, making them appear fascinating during radar scans. Thanks to its unique surface properties and a rich atmosphere containing various organic compounds, Titan's atmosphere becomes an attractive target for future exploration. In 2026, NASA plans to launch a unique astrobiological mission named Dragonfly, set to reach the Moon in 2034. Dragonfly is essentially a flying laboratory resembling a large drone. Its primary goal is to search for signs of life on icy Titan, as scientists believe the moon's conditions closely resemble those of early Earth. Taking advantage of Titan's dense atmosphere, Dragonfly will transport its entire scientific payload to new locations, covering as much surface area as possible for research. The instruments on board will explore diverse areas from extensive carbon dunes to crater bottoms where liquid water and complex organic molecules might have existed, maybe even coexisting for tens of thousands of years. Moreover, Dragonfly will investigate the moon's surface and atmosphere properties and search for evidence of a subsurface ocean. Intriguingly, Titan's potential for creating colonies on its surface makes it more attractive than Mars in this context. Despite being located in the outer solar system, Titan is, in a way, one of the most hospitable worlds for humans. The nitrogen atmosphere is so dense that humans wouldn't need pressurized suits, only oxygen masks and warm clothing, as the surface temperature is around -180 degrees Celsius. Additionally, Titan's atmosphere provides excellent protection against deadly cosmic radiation, which poses a significant danger during space travel. Earth's magnetic field shields us from harmful radiation, but Titan's dense atmosphere effectively absorbs these harmful particles. Moving closer to the Sun, we encounter another fascinating world, one of the gas giants of the solar system, Jupiter, and its moon Europa. Europa, one of its brightest moons, is another icy world that may have a subsurface ocean. Europa, being closer to Earth than Enceladus, is expected to be the target of the first true mission searching for signs of life. Discovered by the eminent astronomer Galileo Galilei in 1610, Europa was initially known as Jupiter II until the discovery of Amalthea in 1862, which shifted Europa to the third position among Jupiter's largest moons. Later, Voyager probes in the late 20th century revealed 3 more new moons, and Europa now stands as the 6th moon of the largest planet in our solar system. The icy Europa likely formed from remnants of material orbiting the young gas giant. Interestingly, the Jovian system is often referred to as a mini-solar system because Earth and other planets also formed similarly from gas and dust remnants after the birth of the Sun. With a diameter of 3,100 kilometers, Europa is only 10% smaller than our moon. However, unlike Earth's moon, Europa is significantly brighter, reflecting 5.5 times more light. The composition of Europa's surface, made of water ice, became known in the 1960s through observations from ground-based telescopes. During the Voyager flights, astronomers obtained the first hints that this icy moon might harbor a global ocean of liquid water beneath its surface, similar to its smaller sibling in the Saturnian system. Images captured by space probes depicted a surface crisscrossed with numerous bands and ridges, remarkably lacking significant impact craters and tall mountains. In other words, the surface appeared much smoother compared to other icy moons. Despite Voyager not flying very close to Europa, the images were of sufficient quality for researchers to notice that some dark bands intricately matched like puzzle pieces. Additionally, only a few impact craters were observed, which raised questions since any planetary surface is constantly bombarded by meteorites over billions of years, and thus it should be mostly covered with craters. The absence of these features suggested that Europa's icy crust was relatively young, indicating significant geological activity on the moon's surface. The causes of Europa's geological activity, in a world far from the Sun, are similar to those compelling Enceladus to erupt geysers from its surface. Orbiting Jupiter every 3.5 Earth days at an average distance of 670,000 kilometers, Europa is tidally locked to Jupiter, meaning one hemisphere always faces the gas giant. Notably, Europa, along with 2 other large moons, Io and Ganymede, is in an orbital resonance. This means that whenever Ganymede completes 1 orbit around Jupiter, Europa completes 2 orbits, and Io completes 4. Over time, the orbits of most large moons or planets tend to become more circular. However, in the case of these 3 moons, gravitational resonance causes their orbits to take on a slightly elliptical shape. This occurs because the moons repeatedly align in the same positions within their orbits, exerting a slight gravitational tug on each other, preventing their orbits from becoming circular. As Europa's orbit is elliptical, its distance from Jupiter varies, with the closer side experiencing stronger gravitational forces than the farther side. This difference in gravitational forces changes during Europa's orbit, creating tides that stretch and relax its surface. This internal movement, combined with the gravitational forces of neighboring moons, generates internal friction and, consequently, heat within Europa, a phenomenon known as tidal heating. However, as scientists studied the surface, they noticed that the patterns of ice fractures did not correspond to the expected patterns generated solely by tidal forces. Researchers concluded that Europa's icy crust was moving independently, separate from its interior. This suggested the presence of either a layer of warmer ice or a subsurface ocean of liquid water. These intriguing findings drew astronomers' attention to the Galileo mission, which launched in 1989 and entered Jupiter's orbit in 1995. The mission aimed to observe each of Jupiter's 4 largest moons during multiple close flyways. The information sent back by Galileo about Europa was so compelling that the mission was expanded to include 12 close flyways of the moon. The spacecraft captured images at various scales, revealing new details of the surface. The icy crust was intersected by long linear fractures, some only 1 or 2 kilometers wide but extending for thousands of kilometers across the surface. Some of these fractures formed ridges hundreds of meters high, while others appeared to have split into rows of parallel grooves. Alongside these fractures, a reddish-brown material covered Europa's surface. Its composition is not definitively known, but it likely contains salts and sulfur compounds mixed with water ice, altered by the planet's radiation. The chemical makeup of the surface may hold clues about the moon's potential habitability. Notably, the exploration of Europa's magnetic field was a crucial part of the Galileo mission. Astronomers observed disruptions in Jupiter's magnetic field around Europa, indicating the creation of a unique type of intrinsic magnetic field within the icy moon. This magnetic field suggests the presence of a conductive fluid beneath the surface. Based on Europa's icy composition, scientists believe that the most likely substance to create such a magnetic field is salty water hidden beneath the surface. This, to date, stands as one of the strongest pieces of evidence for the existence of a subsurface ocean on the moon. By the way, it is expected that the thickness of Europa's outer icy shell varies from 3 to 30 kilometers, and the subsurface ocean is supposed to be twice as voluminous and significantly deeper than Earth's oceans. The Hubble Space Telescope, while observing Europa, detected that the moon even has its own atmosphere, primarily composed of molecular oxygen. However, breathing there would be unlikely, as the pressure of such an atmosphere is 3 trillion times less than on Earth. In 2012, Hubble also captured an intriguing image that could be interpreted as a plume of water vapor reaching a height of 200 kilometers, erupting near Europa's south pole. Later in 2018, astronomers confirmed this discovery by reviewing old Galileo mission data. It was initially assumed that these plumes were likely episodic and occurred when Europa was at its farthest point from Jupiter. The only other place in the solar system demonstrating something similar is Enceladus. However, unlike Enceladus geysers, it appears that Europa's plumes emit pure water vapor without the presence of ice and dust. Nevertheless, scientists are still uncertain about the source of these plumes, whether they erupt directly from beneath Europa's subsurface ocean or form in pockets of liquid water, possibly within the moon's crust. In one study from 2020, researchers attempted to model the plumes, challenging the idea of a subsurface ocean. Utilizing archival data from the Galileo spacecraft, the team investigated a crater formed millions of years ago when an object the size of a comet or asteroid collided with the moon. Scientists modeled that the intense heat generated from the impact could have melted a significant amount of ice. While most of the water would naturally refreeze, some of it could absorb enough salt to remain liquid. Due to its increased salinity, this water could move within the icy shell and, due to encountering a particularly porous patch of surface ice, eventually burst out in the form of geysers. If this model of plumes holds true, studying samples of water vapor may not provide answers about the potential for life beneath Europa's surface, as these would not be samples directly from the ocean. However, the exact source of the water responsible for the geysers is yet to be determined, and perhaps NASA's Europa Clipper mission will provide more information. By the way, this mission is the first dedicated mission to search for signs of life beyond Earth, and is set to launch in 2024. So it seems that in the coming decades, Europa will finally reveal its secrets. Moving from the icy desert of Europa, let's shift our focus to the hellish world with active volcanoes, possibly the main highlight of Jupiter's system. The rocky moon named Io is a true volcanic champion. It is the only place in the solar system, besides Earth, where eruptions of molten rock from numerous volcanoes can be observed. Some of its hundreds of fiery craters covering the moon's surface are many times larger than our cities and even regions. Powerful eruptions on Io's surface can create plumes of epic proportions, sometimes reaching heights of almost 500 kilometers. Add to this the intense radiation from Jupiter, and you get one of the most infernal environments we know of. Io is one of the 4 so-called Galilean moons orbiting Jupiter. It is slightly larger than our moon and, in terms of size, is second only to its neighbors Ganymede and Callisto, as well as Saturn's moon Titan. Io boasts the highest average density of any known astronomical object, along with the strongest surface gravity. Moreover, it has the least amount of water of any known object in the solar system. I'll be using the prefix most quite a few times because most of Io's characteristics are indeed unique. Io was the first of Jupiter's moons discovered by the distinguished Italian astronomer Galileo Galilei on January 8, 1610. Galileo, in fact, observed Io a day earlier but couldn't distinguish it from Europa due to the limited power of his telescope. Therefore, initially, both moons were recorded as a single light dot. The discovery of Io, along with 3 other large moons of Jupiter, marked the first instance of finding a moon orbiting another planet besides Earth. This eventually led to the understanding that all planets revolve around the Sun, and the Copernican model of the solar system, where the Sun is the center of our celestial system, became dominant in the 17th and 18th centuries. Initially, Galileo named Jupiter's moons the Medicean planets in honor of the powerful Italian Medici family of that time. Io, along with Europa, Ganymede, and Callisto, were later recognized as significant celestial bodies in their own right. The unique characteristics of Io have made it a focal point of scientific interest. The intense volcanic activity, resulting from tidal heating caused by its gravitational interactions with Jupiter and its fellow moons, continues to shape Io's dynamic and ever-changing surface. The volcanism on Io, driven by the constant flexing and squeezing due to tidal forces, sets it apart as a captivating object for further exploration and study. The peculiarities of Io showcase the diverse and extraordinary nature of the moons in our solar system. He simply called them by numbers from 1 to 4. In fact, such unoriginal names persisted for centuries, and only in the mid-17th century were the names of Galileo's moons, Io, Europa, Ganymede, and Callisto, officially adopted. This decision was made only after it became clear that assigning numbers to the satellites would lead to confusion as new moons were discovered. By the way, in Greek mythology, Io was a priestess of Hera and a lover of Zeus, so Io is not a he, but a she, just like Earth or Venus. Most of what we know about Io comes from space probes rather than ground-based observations. Although no dedicated mission has been sent to this unique moon, several spacecraft have flown by the Jupiter system and, of course, observed its moons. In 1973, the NASA Pioneer 10 spacecraft was the first to arrive, managing to capture the first images of Io. Subsequently, NASA's Voyager 1 and Voyager 2 probes returned to Jupiter in the late 70s. The improved optical systems of these probes provided detailed images, revealing a diverse landscape on Io. Voyager 1, during its close flyby, captured a peculiar, varied terrain devoid of impact craters. The high resolution allowed scientists to identify relatively young surfaces with bizarrely shaped features, as well as mountains taller than Everest. Interestingly, the images also showed traces resembling lava flows. However, more in-depth analysis later revealed not only lava flows but volcanic plumes erupting from Io's surface. Further examination of additional images identified as many as 9 volcanic plumes scattered across its surface. This discovery left no doubt about the significant geological activity on the moon. Although Voyager 2 did not approach Io as closely as its predecessor, a comparison of the images taken by both spacecraft revealed some changes on the moon's surface that occurred in just 4 months between the flybys. Voyager 2 also confirmed that 7 out of the 9 plumes detected in March were still active in July. Around 20 years after the Voyagers, the Galileo spacecraft paid a visit to Jupiter. Its observations, with higher resolution, indicated that there might be up to 300 active volcanoes on Io. The lava erupting on the surface reaches extremely high temperatures, approximately 1500 degrees Celsius. However, due to Io's thin and unstable atmosphere, any generated heat quickly dissipates into space. Consequently, despite constant eruptions, the Moon remains extremely cold, with an average surface temperature of -130 degrees Celsius. Io's intense volcanic activity distinguishes it from Earth's volcanoes. Io's volcanoes are not towering mountains. Instead, they take the form of large pits known as calderas. These are essentially lava lakes, and occasionally lava can overflow and spread across the Moon's surface. Powerful explosions can even propel volcanic material far into space, creating dramatic plumes. An example of such an event is the eruption of the volcano Vashtar, captured in a fantastic sequence of images by the New Horizons probe in 2007. The volcanic material rises to an altitude of 330 kilometers, forming a plume reminiscent of an umbrella. Despite Io's formation around 4.5 billion years ago, its prolific lava production suggests that the age of its surface is no more than a few million years. Io's volcanism is not driven by the heat remaining from its formation or the decay of natural radioactive substances in its interior. Instead, it is a result of specific orbital dynamics within Jupiter's largest moon system. While Io completes one orbit around Jupiter in approximately 42.5 hours, its significant neighbors, Europa and Ganymede, exert gravitational forces that alter Io's orbit, making it more elliptical. This elliptical orbit causes Io to periodically approach and recede from Jupiter, experiencing immense tidal forces, about 20,000 times stronger than Earth's tides caused by the Moon. These tidal forces cause tremendous deformation, creating bulges on Io's surface that can reach up to 100 meters in height. This constant stretching and compressing generates significant internal friction within Io, producing a vast amount of heat, about 20 times greater than the heat flow from Earth. This extraordinary internal heat source is the primary driver of Io's volcanic activity. The intense gravitational forces from Jupiter, the largest planet in the solar system, play a crucial role in this complex dance. Despite its small size compared to Earth, Io, influenced by the powerful gravity of Jupiter, experiences tidal forces that have shaped it into the most volcanically active world in the solar system. The images captured by the Galileo spacecraft provide a closer look at Vashtar. The energy radiated by the lava from an active volcano was so intense that the spacecraft's camera detectors could only register it as a white spot. Another massive volcano named Pell, unfortunately, was not active during Galileo's flyby, but Voyager 1 recorded a massive plume rising above its surface at an altitude of 300 kilometers. This observation confirmed the existence of active volcanism on Io. Undoubtedly, the most powerful volcano on Io to date is Loki Patera. This volcanic depression has a diameter of 202 kilometers, almost the size of the entire Zaporizhzhia region. Loki generates, on average, 25% of the total heat emitted by Io into space. It is interesting to note the mountains on Io, with an average height of 6 kilometers, often appearing as large isolated structures. Despite the significant influence of volcanism on the surface, most Io mountains do not form through volcanic activity. They result from compression in the Moon's upper crust caused by deep-seated shifts. However, what immediately catches the eye when observing Io is its striking surface coloration. Some compare it to a pizza, others to rotting fruits. Either way, the colors are genuinely fascinating and are indeed a result of volcanic activity. The yellow or yellow-green areas around the equator are predominantly sulfur, while the white or gray patches covering almost the entire surface consist of sulfur dioxide frost. At the poles, the coloring transitions to a slightly reddish-brown due to the maximum radiation levels in these latitudes, damaging sulfur molecules and altering the surface coloration. Places with active eruptions also exhibit a reddish hue, attributed to various silicates and sulfur compounds. Io, along with its neighbor Europa, primarily consists of silicate rocks and iron, making its composition closer to terrestrial planets than to other satellites in the solar system, which are mainly composed of a mix of water ice and silicates. Io's average density is slightly over 3.5 grams/Km3, the highest among all ordinary satellites in the solar system. Its core is believed to consist of iron or iron sulfide, surrounded by a mantle rich in silicates. One of Io's most remarkable features is its interaction with Jupiter's magnetic field. Although all 4 Galilean moons have some impact on the planet's magnetosphere, Io's effect is much more significant due to its intense volcanism and the fact that its orbit is only 6 times Jupiter's radius. This proximity places Io within the intense magnetic field region. Io is considered the primary source of charged particles for Jupiter's magnetosphere. The volcanic dust ejected by Io's active plumes interacts with Jupiter's magnetic field, creating a ring of charged particles around the planet. This ring, shaped like a torus, is known as the Io plasma torus. Io's plasma torus is an intensely radioactive region, much more extensive than initially anticipated. Charged particles within the torus create a hazardous environment for both manned and unmanned spacecraft. The Juno spacecraft, currently nearby, primarily focuses on studying Jupiter's magnetic field. However, no missions are currently planned specifically for Io. Nonetheless, the unique features and scientific value of Io make it a celestial body worth exploring in the future. Next year, the European Space Agency will launch a mission called GEOIS, with the primary goal of investigating Jupiter's moons Europa, Ganymede, and Callisto. However, it is expected that the probe will also explore Io, although it will not approach it closely. In 2024, NASA plans to launch the Europa Clipper mission, which aims to study the habitability of Jupiter's icy moon Europa. In any case, we can anticipate new exciting discoveries related to Jupiter's moons. Perhaps on some of them, we might even find signs of life. However, not only Jupiter or Saturn can boast of remarkable worlds orbiting them. When it comes to the satellites of the planets in the solar system, there is one planet that defies our expectations, and that planet is Neptune. Triton, Neptune's main moon, is undoubtedly one of the most fascinating celestial bodies in the solar system, primarily due to its unique characteristics. Triton's orbit is circular and too close to Neptune, yet highly inclined relative to the planet's equator. Additionally, Triton's movement along its orbit is retrograde, meaning it moves in the opposite direction to Neptune's rotation. Therefore, Triton's history is expected to differ significantly from that of regular large moons, such as Jupiter's or Saturn's. Triton was discovered by the British astronomer William Lassell on October 10, 1846, just 17 days after the discovery of Neptune by the German astronomer Johann Gottfried Galle. Upon learning about the discovery of the new planet, John Herschel, the son of the renowned English astronomer William Herschel, who discovered many of Saturn's and Uranus's moons, wrote to Lassell, recommending him to observe Neptune and look for its satellites. Lassell gladly followed the suggestion and, within 8 days, identified Triton. Lassell also claimed to have discovered rings around the planet, although it was later confirmed that Neptune indeed has rings, but they are so faint that it's unlikely astronomers genuinely saw them. Triton got its name 34 years after its discovery in Camille Flammarion's popular astronomy book. However, it took several more decades before this name became commonly associated with Neptune's new moon, and then known as Neptune I. Unfortunately, the only attempt to study Triton's characteristics up close occurred in 1989 when Voyager 2 flew past the Neptune system. Most of what we know today about Triton is based on data from this brief visit of the spacecraft. First and foremost, Triton is the largest moon of Neptune, accounting for 99.5% of all the mass orbiting the planet. Currently, Triton is the 7th largest moon in the entire solar system, trailing behind the 4 Galilean moons of Jupiter and Saturn's moon Titan, and, of course, our own moon. Apart from Triton, at least 13 more moons orbit Neptune, with 7 of them inside Triton's orbit classified as irregular moons. In other words, these are moons with prograde rotation, nearly circular orbits, and almost the same orbital plane as the parent planet. Generally, all large, spherical moons we know of, including our Moon, as well as the massive moons of Jupiter, Saturn, and Uranus, rotate approximately in the same plane as their planets and in the same direction. However, Triton is unique in this aspect. Triton revolves around Neptune in a retrograde orbit, meaning it moves counterclockwise when viewed from above the planet's north pole, while Neptune and other planets rotate in the opposite direction. Moreover, Triton is not even in the same plane as Neptune's rotation. Triton's orbital inclination to the planet's equatorial plane currently stands at 130 degrees, a significantly high value. All these factors suggest that Triton likely did not form from the same circumplanetary disk as the other inner satellites of Neptune. Instead, Triton is more likely a captured celestial guest that gravitationally fell into the distant grip of the icy giant. Satellites believed to be captured by a planet's gravitational attraction are called irregular moons. Typically, these are much smaller bodies than regular moons, have highly eccentric orbits, and often large inclinations relative to the planet's equatorial plane. Additionally, such moons tend to appear 3 to 8 times farther from the planet than the farthest regular moon. However, Triton, besides being large, is relatively close to Neptune, with an average orbital distance of only 355,000 kilometers, about 10% closer than our Moon to Earth. The next moon after Triton, Miranda, is at a colossal distance of 5.5 million km, approximately 15 times farther. Thus, due to its peculiar properties, Triton is indeed unlike regular planetary satellites and stands out even among irregular moons. But what does it resemble, and what is the answer to the dwarf planet? Indeed, Triton shares more common features with Pluto than with other moons. Therefore, the leading theory of its formation suggests that Triton was not born in orbit around Neptune, but rather in the Kuiper Belt, a region beyond Neptune in orbit around the Sun. Furthermore, Triton was once a true king of the Kuiper Belt, being significantly larger than Pluto and any other known object that could have originated there. In addition to its orbital characteristics, Triton's external appearance and internal composition also provide crucial clues about its origin. A significant factor pointing to this is its average density. Other massive moons in the solar system had a wide range of densities, mostly ranging from 2 to 3 grams per cubic centimeter. The densest are Jupiter's moons Io and Europa, while the lower end includes Titan, Ganymede, and Callisto. However, as we move further into the outer solar system, the density of Uranus moons drops to approximately 1.5 grams per cubic centimeter. This is because most of the moons around the ice giants are primarily composed of water ice, which has a relatively low density. Triton, with a density just above 2 grams per cubic centimeter, stands out as anomalously high. Interestingly, the only other inhabitant of these outer reaches with a defined density is Pluto, and Triton is even denser. Consequently, Triton is expected to have a more compact core made of rock and metal, making it more comparable to the most massive object in the Kuiper Belt, Eris. In this context, Triton is perhaps better compared to the most massive representative of the Kuiper Belt, Eris. Notably, the high density of these celestial bodies suggests that the composition and formation conditions of inhabitants in the outer solar system differ somewhat from those in the circumplanetary nebulae from which regular moons formed. This reinforces the argument that Triton originally formed in orbit around the Sun. Triton, although discovered shortly after Neptune, remained a mystery until the era of modern telescopes. The vast majority of information we currently have about Triton was obtained during the encounter of Voyager 2 with Neptune in 1989, when the spacecraft also decided to fly by Triton, similar to Voyager 1's journey to Saturn and Titan. Due to the speed of Voyager's visit and Triton's slow rotation, only one hemisphere covering 60% of the surface was clearly visible in the images. The rest was either in darkness or appeared blurred. Nonetheless, the spacecraft managed to capture several clear photographs of the Moon's surface and determine some previously unknown characteristics. One of Triton's most prominent surface features is its remarkably youthful geological landscape. Impact craters, dominant in the topography of most other moons, are extraordinarily rare on Triton. This scarcity could result from significant geological activity on the Moon. Triton boasts a relatively flat surface, with observable relief changes not exceeding 1 kilometer. Moreover, photographs reveal evidence of cryovolcanic activity, creating flows of frozen materials that inundate and level parts of the surface. This phenomenon resembles how lava eruptions on Earth lead to solidified, vast plains. However, instead of molten rock, Triton's cryovolcanism involves liquid water erupting and freezing on the surface, forming extensive icy plains. Besides plains, Voyager 2 also observed ridges and grooves on Triton's surface, indicating tectonic fractures and fissures. The landscape somewhat resembles the surface of another geologically active moon, Europa, as well as Pluto. Like Pluto, most of Triton's surface is covered with frozen nitrogen, as well as water ice, commonly referred to as dry ice. Despite the frigid conditions, Triton's surface has a reddish tint, attributed to methane ice reacting to sunlight, producing tholins, organic compounds with a tar-like consistency. However, the presence of organic compounds does not necessarily imply the existence of life. Organic compounds are fundamental chemical substances from which life is believed to originate. Nevertheless, due to Triton's extremely cold surface, life as we know it cannot exist there. However, something interesting may lie beneath the surface of Triton. The density of Triton indicates that its internal structure consists of a solid core made of metals and rocky mantle composed of ice and crust. In Triton's interior, there should be enough rocky materials for radioactive decay, providing heating and convection in the mantle, possibly supporting a subsurface liquid ocean, similar to Jupiter's moon Europa. The predicted existence of a subsurface ocean may imply the potential for life in this distant and cold world. Another notable feature on Triton's surface is its massive southern polar cap, extending almost to the equator. A similar cap is expected at the North Pole. Voyager's cameras detected eruptions of gaseous nitrogen and entrained dust from beneath Triton's surface in the polar region, resembling geysers. Triton becomes the fourth known moon with active eruptions on its surface. The plumes on Triton are relatively modest, rising about 8 kilometers above the surface until winds blow their tops away, leaving long, dark streaks reminiscent of industrial smokestacks on Earth. Several models explain these eruptions, suggesting that Triton's surface likely comprises a semi-transparent layer of frozen nitrogen beneath which lies a darker substrate. Since geysers were detected where solar light intensely influences the surface, solar radiation likely penetrates the thin surface layer, slowly heating and vaporizing subsurface nitrogen. The pressure from accumulated gas increases until it erupts as a geyser. This mechanism is thought to be similar to the formation of spring CO2 geysers on Mars. If Triton is indeed a captured dwarf planet that Neptune once snatched, the question arises as to how Neptune managed this capture. For a planet to capture a passing space object, that object must lose enough energy to slow down to a speed less than that needed for escape. The leading hypothesis suggests that before its capture, Triton was part of a binary system similar to Pluto and Charon. Such systems are quite common in the Kuiper belt. When Neptune approached this binary system, interactions between them could have unfolded in a way that expelled Triton's former companion, while Triton became gravitationally bound to Neptune. Interestingly, this event likely had a significant impact on Neptune's moon system. The 7 inner moons of Neptune, from Naiad to Proteus, are likely the only surviving moons from the original system of inner moons. Triton's gravitational influence could have scattered or disrupted all other large moons. Perhaps some of them still exist as centaurs or long-period comets, or they were simply torn apart by Neptune's gravity. While many of these questions remain unanswered, future missions to the ice giants could provide more insights. As for Triton's fate, being a captured moon, it will eventually be lost forever due to the nature of its orbit. Triton will eventually spiral into Neptune's gravitational well and disintegrate into fragments. This is estimated to happen in about 3.5 billion years, leading to the formation of a new massive ring around Neptune, similar to Saturn's rings. However, all these particles will eventually be absorbed by the planet. Therefore, there is still plenty of time for us to learn more about the distant icy world that awaits new discoveries. Now, let's return to Jupiter, where an intriguing moon that could easily be mistaken for a planet orbits. If it moved around the Sun, it would undoubtedly be considered a planet. I am referring to Ganymede, Jupiter's largest moon, which hosts a massive subsurface ocean of liquid water beneath its surface. For a long time, we knew very little about Ganymede, but thanks to detailed photographs of its surface and other data from numerous spacecraft, the moon is gradually revealing its secrets. Of course, any discussion about Ganymede should begin with the fact that it is indeed a gigantic moon. It is nearly twice the size of our moon and, with a diameter of 5270 km, holds the title of the largest moon in the entire solar system. Moreover, Ganymede surpasses even the planets Mercury and Pluto in size and is only slightly smaller than Mars. In other words, Ganymede could easily be called a planet if it orbited the Sun instead of Jupiter. In fact, in the list of solar system objects ordered by size, including the Sun, Ganymede would rank ninth. Discovered in the 16th century by the Italian astronomer Galileo Galilei, Ganymede is one of Jupiter's four largest moons, along with Io, Europa, and Callisto. Three of them were first observed on the same day, January 7, 1610, when Galileo gazed into the sky through his recently improved homemade telescope. The fourth moon was identified the following night. Initially, Galileo thought he was seeing stars, but observing them through the telescope for several nights, he realized these stars were moving in a different direction from the background stars, changing their positions relative to each other every few days. Galileo concluded that he wasn't seeing stars, but rather moons orbiting Jupiter. This discovery eventually led to the understanding that planets revolve around the Sun, not the solar system around the Earth. The moon we now know as Ganymede was initially called Jupiter AE, denoting it as Jupiter's third moon. However, in the mid-19th century, astronomers decided to move away from numerical designations, and the moon was named after Ganymede, the Trojan prince in ancient Greek mythology. The myth narrates that Zeus, taking the form of an eagle, transported Ganymede to Olympus, where he became the cupbearer of the Olympian gods and, of course, the latest romantic interest of the Olympian ruler. Situated over 1 million kilometers from Jupiter, Ganymede is the seventh farthest moon from the planet and the third among Galilean moons. It completes one orbit around its planet every 7 days and 3 hours, similar to the majority of known moons. Ganymede is tidally locked to Jupiter, meaning one of its sides always faces the planet, resulting in a Ganymedian day lasting 7 days and 3 hours. The first close-up observations of Ganymede were made by the Pioneer 10 spacecraft in 1973. However, it passed through the Jupiter system at high speed, so the image quality was not ideal. Nevertheless, even this data was sufficient for scientists to estimate some characteristics of the little-known moon. Voyager 1 and Voyager 2 spacecrafts studied Ganymede during their passage through the Jupiter system in 1979, providing the first images of the distant icy satellite's relief. Thanks to the Voyager data, scientists could make precise size estimates for Ganymede, revealing it to be larger than Saturn's moon Titan, which was previously considered the largest moon in the solar system. However, the best data about Jupiter's moon could only be obtained from a spacecraft orbiting Jupiter, and the first of such missions was the Galileo spacecraft. It entered orbit around the gas giant in 1995 and, between 1996 and 2001, conducted 6 close flybys of Ganymede, revealing some unusual features of the moon's surface. Ganymede's surface is characterized by 2 types of terrain: dark and slightly lighter regions. Dark areas cover extensive areas and are separated by bands of lighter relief. Both types of terrain bear impact craters, but the dark regions have a higher crater density, indicating their older age compared to the lighter part of the surface. The estimated age of the dark areas is approximately 4 billion years, suggesting that this region has preserved its features from the early stages of the moon's evolution. In general, Ganymede's surface, like that of other solar system bodies, contains dark relief that occupies about a third of the surface. Besides ice, it includes clay and organic compounds, likely indicative of the chemical composition of numerous planetesimals from which Jupiter's satellites formed. Impact craters on Ganymede generally have much shallower depths than craters of similar size on rocky bodies such as the Moon or Mercury. Likely, this is associated with the characteristics of Ganymede's icy crust. The ice may not be very hard, allowing it to subside and somewhat level the relief. Meanwhile, the brighter part of the surface has a more icy composition than the dark one and is covered with intricate patterns of long and narrow grooves. The depth of these grooves is usually a few hundred meters, and they can extend for hundreds of kilometers. They often lie in parallel sets, with adjacent parts located at distances of 5 to 10 kilometers from each other. This pattern somewhat resembles the surface of another Jupiter moon, Europa, with its bright relief covered in similar natural channels. Presumably, this relief was formed during a period of tectonic activity when internal compression destroyed the crust, causing fractures. The exact time of such activity is unknown, but the density of craters in the bright region indicates that it occurred in Ganymede's early history, though later than the formation of the dark areas. The heating mechanism necessary for creating the required level of tectonic activity for such relief formation is still unknown. Scientists lean towards the hypothesis that the activity occurred due to tidal heating, when the moon could pass through unstable orbital resonances in the past. Orbital resonance is what connects 3 out of 4 Galilean moons: Io, Europa, and Ganymede. Each time Ganymede completes one orbit around Jupiter, Europa rotates twice, and Io completes 4 rotations around the planet. Such resonance significantly enhances gravitational interactions between them, significantly affecting their orbits. For example, Io and Europa, due to resonance, have slightly eccentric, elongated orbits, periodically approaching and moving away from the planet. This gravitational interaction literally stretches the moons when they approach Jupiter and compresses them when they move away, changing their shape. Such constant deformations force heating from within, like kneading plasticine, generating heat due to the friction of material deep within the moons. Io, in particular, experiences the most extreme deformation, with constant stretching and squeezing up to 100 meters. It is the most geologically active body in the solar system. Contrary to Io, Ganymede has an almost perfect circular orbit with very low eccentricity. Hence, tidal heating for this moon should be minimal. However, in the past, Ganymede might have passed through other types of resonances that could stretch its orbit. In such a case, tidal flexing of the ice could also heat Ganymede from the inside, causing tension in the lithosphere. This tension could lead to the development of cracks and fractures that, in the past, might have erased a significant portion of Ganymede's old dark relief. Interestingly, astronomers using the Hubble Space Telescope found evidence of a very tenuous, finite atmosphere on Ganymede, consisting of oxygen. However, its pressure is billions of times lower than Earth's atmospheric pressure. This oxygen is not considered evidence of life on the moon. It is believed to form when water ice on Ganymede's surface breaks down into hydrogen and oxygen under radiation. Hydrogen, being lighter, quickly escapes into space, leaving oxygen in the moon's thin atmosphere. In 2021, thanks to observations from the Hubble Space Telescope, scientists detected traces of water vapor in Ganymede's atmosphere. However, unlike its neighbor Europa, water vapor on Ganymede does not erupt from beneath the moon's surface in plumes. Instead, it is likely a result of sublimation caused by the heating of icy areas on the surface. Sublimation is the process where a solid material transitions directly into a gas phase without passing through a liquid phase. In this case, it is believed to be triggered by temperature changes near Ganymede's equator. By the way, the surface temperature of the moon varies from -182 to -12 degrees Celsius. That is, it is always cold here, as Ganymede is far from the sun and lacks a dense enough atmosphere to retain the warmth of the few sunlight it receives. However, observation data shows that the moon is warmer in certain regions and at certain times of its day. Ganymede is mainly composed of silicate rocks and water ice, with a rocky layer forming its mantle and a relatively small iron core beneath it. The estimated thickness of the icy crust may be up to 150 kilometers, below which there is likely a global ocean of salty water. Ganymede is considered to be another icy oceanic world in the solar system, at least according to data from the Galileo spacecraft, which detected Ganymede's magnetic field in 1996. In 2015, the Hubble Space Telescope, observing polar auroras on the moon, confirmed the presence of a subsurface ocean. This large saltwater ocean influences Ganymede's magnetic field and, consequently, its polar auroras. Scientists calculated that the thickness of the subsurface water layer should be approximately 100 kilometers, roughly 10 times deeper than Earth's oceans, containing more water than all of our planet's oceans combined. However, it is premature to imagine a turbulent life beneath Ganymede's icy surface. In this context, Europa is more promising for potential extraterrestrial life. The reason is that Ganymede's ocean is so deep that the water at its bottom, under immense pressure, must compress into a solid state. Life in the deepest parts of our ocean survives due to minerals ejected from geothermal sources, where water directly interacts with rocky formations. Considering the thickness of the ice layer between the rocky mantle and water, it is unlikely that something similar can occur on Ganymede. Nevertheless, some computer models predict that inside the moon, ice and oceans could be arranged in several layers like a sandwich. If this were true, the innermost layer could indeed contact the rocky mantle, increasing the chances of life. However, the most remarkable feature of Ganymede is its unique magnetosphere. Discovered by the Galileo mission, Ganymede's magnetosphere is unique among moons in the solar system. Only two other solid bodies, Mercury and Earth, can generate their magnetic fields. Considering Ganymede has a metallic core, its magnetic field likely forms similarly to Earth's, resulting from the movement of molten, conductive material in its interior. However, even the presence of a metallic core does not provide scientists with certainty about the origin of Ganymede's mysterious magnetosphere. This is especially puzzling since Ganymede is the only moon with such characteristics. Additionally, considering Ganymede's size, it should have long since lost the necessary heat to maintain a molten core. For instance, Mars, although larger than Ganymede, has already cooled down, lacking its own magnetic field. One explanation for Ganymede's persistent magnetic field involves the orbital resonances that likely influence the moon's geological activity. Tidal heating of the mantle could have intensified during resonances, leaving the satellite's core convective. However, whether this is true remains uncertain, and more data is needed. Perhaps the GUEV mission will help unveil some of Ganymede's mysteries. The European Space Agency's spacecraft, planned for launch in 2023 and expected to reach Jupiter in 2031, will primarily investigate the icy Galilean moons, including Europa and Callisto. However, the main goal is to study Ganymede, and in December 2034, the spacecraft is set to enter orbit around the largest moon in the solar system. Essentially, it will become the first spacecraft to orbit a moon of another planet. The radiation levels on Ganymede's surface are significantly lower than on Io and Europa, allowing GUICE to orbit directly around the moon without risking damage to its electronics due to intense radiation. So, while we await the launch of new missions to Jupiter's icy moons, most of Ganymede's secrets will remain just that, at least for the next 10 to 12 years.